we continue. Now we continue our considerations with the structure of local time of a Gaussian random process or field. You remember that main object which we are studying is the following expression. This is integral with respect to some domain D. Here is a delta function, 0, some random field psi 0, D. Here is psi is a random field which is defined on the domain D in R and active to R. And when n we suppose y0 and we already discussed that this formal expression can be properly defined like a limit when we substitute a delta function by the some family of function approximating it. Namely, we discussed that those expressions can be written as follows. We use that one constant depending on the dimension n, epsilon and power indicator both radius epsilon at the center in y0 tends to delta y0 when epsilon tends to 0 plus. So we substitute this expression here, and we discussed already that existence of the limit, which is non-trivial, of course, if it is at least positive with positive probability, means in particular that our random field psi visits this point yz. So we decide to study the structure of this expression. In order to do this, we considered last time case when we have delta function from a Gaussian random value. Namely, what we did last time. Instead of this complicated expression, we considered a Hilbert space H, and here is eta, which is white noise. Gaussian white noise. Namely, this is a family of random values organized as follows, like H eta. I denoted as usual scalar product, when H belongs to H prime, H capital, and then we know that this jointly Gaussian family such that expectation of H eta is equal to 0, and covariance and expectation of the product H1 eta multiplied H2 eta is equal to H1 H2. Such family of Gaussian vector waves is called by white noise, and we considered a special case of such expression, namely we considered delta function at point y. We discussed one-dimensional case, so I do not use here arrow. Y now is a number at point y from the random variable h eta, in a case when h has norm equal to 1. So we consider the case norm of h is equal to 1. And in this case, we got a formal expression for this random variable in terms of Hermite polynomials from this h. Namely, it was such formal, I insist, formal series like the sum from 0 to infinity. Here, 1 n factorial. Here, e minus y squared divided by 2t, excuse me, divided by 2, and here is square root of 2 pi, and here we have h n of y multiplied by h n of h n of h eta. Here h n are Hermite polynomials. Let me recall you the formula. H n can be directly defined as follows. It is minus m squared and minus 1 power e x divided by x squared divided by 2 multiplied by d dx in power applied to the function of this kind. And we already discussed that Hermite polynomials organize or complete orthogonal system with respect to standard Gaussian measure. So any random variables which is integrated in square can be expanded in the series of Hermite polynomials of such kind with some coefficients. Now, this is just formal series. We know that these coefficients do not converge in square, so we haven't random variable. This is formal expression. But we discussed that we actually don't need such expression itself. We will have some integrals. So let us recall what we need and try to understand how to get a bridge to those aims. Let me recall you that here water with such expression. Here is delta y0 prime arrow. Here is xi u and d. Which is difference. Yeah? We have additional integral. Maybe we can manage the vector case, but still we have the random field which depends on u. So let us try to expand the situation related this case, one more general case of Gaussian random field. I will consider firstly scalar random field. So I consider such a case where we have only one dimension there. Of course, we suppose that m is less, but now just forget about this for a moment and consider a case where we have multi-dimensional parameter. We can have it. It does not matter right now what is the dimension of the space of parameters of our random field. But we have just one-dimensional random field. Then we said that Xi is Gaussian random field. How we can produce Gaussian random field using our white noise? I told you that we have such a like standard infinite dimensional Gaussian vector. This is white noise eta here. So how we can construct Xi of U that U belongs to using this one? It is very easy. It occurs that it is very easy to do this. Namely, let's consider a function h now, which is active from the domain D to the Hilbert space H. And now, if we have such function h, then one can try to define the Gaussian random field as follows. Psi of U is equal by definition to the scalar product H of U onto here is the definition of our Gaussian random field. It is trivial that it is trivial to check that it is Gaussian. And now let us consider the expression with theta function which we want to study. Then the integral with respect to domain of parameters, our delta function y from Xi of U du is equal to integral over the space of parameters delta U, delta y. Here we have h of U eta and du. Now one can see something familiar here. Yes, this is more or less expression which we studied. But there are few problems. The first one is we consider it only special case when h has a norm equal to 1. Now we don't have such condition. This is one. Another one is much more complicated and is related to our previous considerations. As you remember, we expanded this expression at this formula as a series of the kind. Here is some coefficient multiply on hn from h now u eta. But what happens if we integrate this expression over domain D with respect to parameter U? Will we have some good orthogonal structure? Will we keep it or not? So these are questions which we need to discuss before we get a right expression for local Gaussian local types in terms of orthogonal expansion. Let us introduce universal orthogonal expansion related to our white box. So this will be a first step which we will do today. So we start again from our space A and our noise eta. Let me consider some orthogonal basis E. K is greater than 1. It will be orthogonal basis. Orthogonal basis. Let us denote by eta k the product E k eta. Then one can check that these are standard normal variables. It follows from covariance related to eta and the fact that the element of the orthogonal basis have norm equal to 1 exactly. And also we know that now expectation eta k, eta j is equal to 0 when k is not equal to j. So when they are non-correlated, they are non-correlated when the indices are different. It means that our random variables are not are independent. Yes, you remember the most important property for Gaussian random variables that if they are jointly Gaussian and uncorrelated, they are independent. So we have the coordinates, roughly speaking, of our vector white noise theta, and this is just IID sequence. This is IID sequence of standard normal values. Now let me introduce the notation related to the products of this random variables. I will consider such an expression. Eta k1, here I will put star, and so on. Eta kn is equal to, by definition, by definition. It is equal to h L1 from eta E1 A1 E1 multiplying H A M from eta EM where H are Hermite polynomials. So HA are Hermite polynomials. E1 EM are distinct numbers among this one K1 K1 and finally one is a number of repetitions of I1 among K1 K. So what we are doing, we consider the product, for example, eta 1 multiply eta 2 multiply eta 3 multiply eta 1 eta 2, and then consider distinct numbers from this set. So it will be 1, 2, 3. Then if we put here stars, it will be, you see, we have eta 1, eta 1, eta 1 3 times. Then we must put here not eta 1 in power 3, but H3 Hermite polynomial of degree 3 from eta 1. Then the same we do for eta 2 and eta 2. So we have here H2 from eta 2. And finally, we have just one eta 3. So we multiply by eta 3 because the Hermite polynomial of degree 1 is exactly the random. Yeah. So this is a procedure of substitution of degrees of our coordinates by the Hermite polynomials of the same degree. It is, by the way, a partial case of so-called weak product, and there is a well-developed technique related to weak product, but we don't need it. We only need such expression here, and then it is interesting that now one can say one can say that the set of all such products, so if you consider all such products, eta K1, eta Kn, where n is less or equal than 0. I put 0 here with usual supposition that when we have n equal to 0, we just have constant 1. But when n is greater than 0, we can choose arbitrary K1, Kn, which is equal than 1, such that organize orthogonal basis in the space with an orthogonal basis in the space I will denote it by A2 eta. What does it mean? It means that we consider here all square integrators. Random variables, measure which respect to eta. So we have a basis in our space. Now we can consider more complicated expansion than only with respect to Fermi polynomials from one standard normal y. But before to do this, let us introduce some good notations. So let us organize elements of our orthogonal basis in some groups. Mostly, we organize these groups according to degree. Of course, if degree of our polynomial is equal to 0, then it is just constant. If degree of our polynomial is equal to 1, then what it can be? It is just eta 1, eta n, and so on. And their combinations. Yes. So in this case, we have combinations. From k equal 1 to infinity. Here is alpha k, eta k, and this is nothing else than some h eta. Yes. So now, when we consider some polynomial of the first degree, organized from element of our basis, it is just the products of elements of our space with the white noise eta. So we have this expression for H equal the sum K equal 1 with infinity alpha K EK. Now consider degree equal to 2. It becomes to be interesting. What kind of polynomials from the coordinates of our vector we can have here? First of all, we have polynomials of such kind, IH2 from eta k. And it is equal to eta k squared minus 1. Also, we have polynomials of such kind, eta k, eta A, when k is not equal to a. Yes, this is also polynomial degree 2, and I can put here dot, but I can put here star. It is the same because they are independent, they are different, and by our definition, this weak product is equal to Hermite polynomial degree 1 eta k and Hermite polynomial degree 1 from eta l. So it does not matter what I write here. Then we have such an expression, and one can imagine that maybe the all polynomials degree 2 which are orthogonal to this first degree and 0 degree are of the kind like double infinite sum, say k1, k2 from 1 infinity, and here are some coefficient alpha k1, k2. I will write here eta k1, just eta k2. Then this notation covers both cases, this one and this one. But we have to check what condition this coefficient alpha k1, k2 must satisfy. In previous case, you see, it was they were coordinates of element h, and the series of squares must converge. Here, one can check that exactly the same condition holds, must hold for the sum to be convergent in the square. So we have to say that the sum k1, k2 equal 1 to infinity alpha k1, k2 squared must be less than. Also, it is trivial that it is enough to consider only symmetric alphas, yes, with respect to permutation of coefficient, because our definition of weak product is commutative. So, weak product for etas is commutative. So one can suppose that alpha k1 k2 must be equal to alpha k2 k1. We have two such conditions, and maybe some of you who remember functional analysis recognize this condition. We already met it in functional analysis, in quantum physics, when we consider infinitely dimensional matrices with such condition. This Hilbert-Schmidt methods or Hilbert-Schmidt operator. Yeah? One can consider Hilbert-Schmidt operator. I will call it 4. Why? Because we will consider the case when here are not only 2 indexes, but 3 or more. Then it is non-convenient to say that this is operator, because operator, like matrix, always is active from one space to another. But when we have a lot of directions, K1, K2, and so Kn, then it is not convenient to say that this operator. It's better to say that this is 4. And I will put 4, and this is the sum from K2, K1 equal 1 to 15, alpha K1, K2, and here is tensor product Ek1 and Ek. This is a very simple one-dimensional operator in our Hilbert space. Let me express it. Namely, F tensor product of J acting on some element H is equal to J H F. This is linear one. So we see how we can consider our expression, and moreover, I will use such an expression, K1, the sum which we discussed to infinity, alpha K1, K2. Here is eta K1, weak product eta K2. I will denote, this is a definition. A2 from eta, like our linear form from the non-existent random, formal random element eta in our space. It is just convenient notation, nothing else. This is its definition. So now maybe one can imagine what happened if we consider much more degrees. Let me show you general situation. This general situation where degree will be equal to n, then we can consider such sum from K1, Kn equal 1 to infinity, alpha K1, Kn, and here is eta K1, excuse me, weak product eta K2, eta Kn. And also we require that the sum from K1, Kn equal 1 to infinity. Alpha K1, Kn square is less than infinity. And we can see, we also suppose that this set alpha, that it is symmetric under permutation. Kn is equal to alpha K sigma 1, K sigma n when sigma is taken from the group of permutation of the first nature atoms. So we have such conditions. Then we can define again Hilbert-Schmidt symmetric form AN as a sum of tensor products K1, Kn equal 1 to infinity. Here is alpha Kn, K1, Kn multiplied by tensor product E, K1, E, Kn. And then we can again define, I insist that this is just definition. We can define that An from eta eta is equal to this relation, this expression. So now we have the sets of orthogonal elements in the space of square integrate random variables measured with respect to initial values eta. By the way, this is not easy result, but it is important thing. By the way, this set does not depend on the particular choice of orthogonal basis En. It is important. This set does not depend on the particular choice of this initial orthogonal basis En. Now we can conclude the following interesting thing: that if we have this expression d, here is delta function y psi u du, then it is equal the integral with respect to d. Here we put delta y, here we put this h of u eta du, and we can continue now. We know that this expression has at least formal expansion in terms of those Hilbert-Schmidt forms which we considered, and it is equal to integral with respect to d. Here is the sum from n equals 0 to infinity, and here we have an which depends on u. This is parameter alpha, and eta. And here we have n eta, and here we have the u. Now, what we are going to do? We are going to interchange this sum and this integration. And what we will get? Let us formally continue. Suppose that everything is good, so we can interchange our sum integral, and we will have the sum from n equals 0 to infinity integral with respect to d. Here is an u eta du. Okay. And it's interesting that this way is working. And it happened in good cases that one can calculate this and we get sum of orthogonal summa, but sum which is convergent. So maybe it is a time to consider some examples, because the material of the previous lecture and this one is more or less abstract. So let us consider example where we can calculate exactly all of these things and to check that this series will converge. I will consider maybe the simplest, but not non-important. This is a very well-known example of the local time for Brownian one-dimensional motion. Let us consider such example. Here I will use the notation which we use usually for Brownian motion. So in this example, I will suppose that Wt t belongs to 0, 1 is one-dimensional linear process. It means that it is Gaussian all sets of its finite dimensional finite values, so Wt1, Wt2, Wtn are jointly Gaussian value values, and expectation of t is equal to 0, and expectation of Wt, Ws is equal to minimum Ts. In the sequel, I will denote it by T minima S like this. It's much shorter to write it. Using this characteristic, one can check that W has independent stationary increments, independent stationary increments, and its increment has the same distribution W T plus S minus Wt is distributed like a normal variable with 0 linear components. Now, what we are going to study, this is an integral from 0 to 1 delta y Wt d. This is the object which we consider, and according to our previous consideration, we want to have Hilbert space and white noise. It occurs now that we can define this Hilbert space as follows. Suppose that the Hilbert H is the space of square integrated functions where the interval is 0, 1. Now, what is the white noise there. Let us try to define it as follows. You remember, we have to consider all such products for H. Now this is the function from H2 0 1. Let me introduce this white noise by the formula. H eta. No, formally, eta will be a derivative of W. Why I'm saying formally? Because it can be checked, but it is not again such consideration in our course. I think that most of the audience knows this fact, that W has no derivative as probability 1. So what is it? What is it? But it is interesting that we can calculate such a product with W dot. Namely, everybody know what is the product in this space. If W dot is a usual function, then such a product H W dot must be equal to integral from 0 to 1 Hs W dot S ds. But we just said that there are no AW. But what can we can say that this is just dWs. And it is a fruitful idea. So now I propose to you our white noise, and it will have an expression like the following. H eta is the integral 0 to 1 Hs dWs. This is so-called linear integral with respect to linear process. Why it is called linear integral? Because H is deterministic function. It is deterministic function. In case of when H is a random function, there are different approaches to integrals with respect to W, which leads to deep theory, like Ito integral, most widely distributed, Satonovich integral, mostly used in physics, and extended stochastic integral, which is used like a generalization of Ito integral for non-adapted random functions. But in our case, we only need this integral for deterministic feature. How one can construct it, at least briefly? Like this. Just take H equal to sum from k equal to 0 to minus 1, AK indicator TK plus 1. So I took the partition of the interval 0, 1 on some intervals. Here is T0, T1, and so on, Tn, and then take a step function like this one. And so on. Yeah, this is such H. Then it is nature, and this is, I think, only one so-called only one way which we can support to different arguments to define such an integral from the step function by the sum from k to s0 minus 1 ak is here w k plus 1 minus k, and then we will get immediately that this h eta has a normal distribution with 0 near and norm of h square is a values. It is enough to expand this definition to all h bilinearity approximation to all h from L to 0, 1. So one can easily construct white noise in this case. We already have it. Let us continue and discuss what will be now the representation of our WT. It is also easy. WT now is the product in indicator 0T and our noise. So what we need now, we also need these forms AN, eta, eta. And it is interesting, but rather technical stuff that one can have a very good representation for AN. It occurs that having symmetric Hilbert-Schmidt form AN on our space, let me recall that our space H is the space of square integrated functions. So when I have Hilbert-Schmidt form on this space, it is nature to represent it not by matrix. You remember, we generate this form using infinite metrics, which are symmetric under permutations, and Hilbert-Schmidt, it means that the sum of coefficients in square is finite. But it is nature to represent now on such space Hilbert-Schmidt form by the kernels. So one can have here kernel AN from T1 Tn, which is symmetric AN from T1 Tn is equal AN from T sigma 1 P sigma n. Under permutations, sigma is from the space from the group of permutation, and such that the integral n from 0 to 1 an P1 Tn square dt is 5. This is the analog of symmetric Hilbert-Schmidt matrix. We have symmetric kernel and we have Hilbert-Schmidt condition. And it occurs that now one can express the AN eta like integral from 0 to 1 AN Tn T1 Tn dw1 dw. Of course, this is a rather complicated expression because you remember I mentioned that the simplest way to define the integral with respect to w is the integration with respect to is the approximation by the step function. Here, if you do it, you will get some difficulties, because you see the limits of the integration are such that we cannot use the independence of the increments of inner walls. In order to avoid this, people say this is just formal expression which is defined as follows. This is n factorial multiply on the integral on the simplex. 0 is less or equal to t1, less or equal than tn, less or equal than 1. And here is an, t1, tn, and here is t1, tn. When we consider such kind of integral, it is properly defined and has a good properties. And now we understand that what we need to discuss. We need to discuss how to express a delta function from Wt in terms of such multiple Wiener integral. We will call it in this case not by the general words. This is Hilbert-Schmidt symmetric form from the white noise. We have a particular case. When we study Wiener process, so we will say expansion in terms of multiple Ito-Wiener integrals. So all what we need is just to have an expression of delta function and to understand that we can integrate it. We will do this next lecture. Today we finish our work. Thank you for attention. Maybe somebody have questions, please. Okay, if there are no questions, see you next Monday.